So today we're going to be tackling a problem where we are given certain parameters for a CSTR. It's a continuously stirred tank reactor. And the problem is we have a jacketed CSTR. So let me sketch one out here real quick. A jacketed CSTR. So this means that we have some layer in between the tank surface on the inside, which is in contact with our process. So, we have some process. This is our agitator. It's continuously stirred. And we have jacketed cooling water flowing in and out of the tank jacket, as well as a volumetric flow rate coming in and out of the tank. So throw this out here. Why not? So the problem proceeds as such. We have cooling water at 300 Kelvin, and we have a flow in, so toss in a Q in, a Q out, as well as a concentration of our process here. We'll call this concentration of species A. And our reaction is defined by this first order irreversible reaction, where we have a species A going to a species B. And what we are trying to analyze here is the effect of changing this cooling water temperature, adjusting it to be higher or lower than its original set point, and how does that affect the concentration and temperature of our CSTR system. So the first thing that I'm going to do here is I'm going to throw out a mass balance. Now a mass balance in this problem might look something like this, where we're taking with the differential with respect to time of our volume times our concentration. And the reason that we might do that is, well, if we look at units of volume, that's going to be liters in this problem. We look at units of concentration, we're going to have moles per liter, as you can see up here. So volume is in liters, concentration moles per liter. So that gives us a final value of moles, which can be translated to mass, but we'll keep it in moles in this for our mass balance. And essentially, our mass balance, if I can find my pointer. Oh boy. Our mass balance, we're going to be looking at the difference in our flow rates. So going in, we'll have, let's call it the flow of species A through the inlet times the concentration of A through the inlet. For the same reason, we want to make sure these units match up, so we're going to multiply our volumetric flow rate by our concentration, which will give us our molar flow rate. And we'll do the same for our outlet, so Q outlet times Q CA at the outlet. Now, remember that I said that this was a first order reaction that we have over here. This is a first order exothermic reaction, and I mentioned that because that's something that'll help us with the energy balance when we do it later on. The rate for a first order reaction takes the general form, so takes the general form of K times CA to the first power for the first order. This K is our rate law constant, which is defined by an Arrhenius equation that looks something like this. Minus E over RT. Where K naught, this is our maximum reaction rate. Maximum reaction rate. We have E our activation energy, R is our gas law constant, T is our absolute temperature. So how are we supposed to implement this into our mass balance? Well, we can have plus KCA, and right now this has units of moles per liter, or yes, moles per liter per minute. So K is minutes reciprocal, as we see here, minutes reciprocal. So in order to get this into moles per liter per minute, or sorry, moles per minute, from moles per liter per minute, we will add a volume term right there. So now we see that our volume is going to be constant in our tank. That's defined in our problem. So we'll do something like V dCA dt is equal to, we're assuming that our CSTR is at steady state, meaning that Q in equals Q out equals Q. So I'll just put Q here, QA, why not, times CA in minus CA out plus volume times the reaction rate constant times the concentration of A. Now the next thing we're going to do is do our energy balance, but before that, make a little fix here. This should be minus. Our reaction rate's taking away from species A. I'm going to divide both sides by volume, so our final mass balance will look something like this. I'll just name this Q, QA, Q, doesn't really matter. CA in minus, we'll call this CA because it's going to be the concentration of A at the outlet at any time T, minus KCA. So this will be our mass balance that we can use Python to manipulate and solve for our concentration. Now the next thing we want to solve for is our energy balance. So our energy balance is going to rely on temperature. We know that. So we're going to have some differential temperature with respect to time. But we also know that we want this in terms of joules. So we are given our specific heat, not to be confused with the concentration. We're given the specific heat, and the units for our specific heat, let me just do this down here, is equal to joules per joules per gram Kelvin, not mole Kelvin. Joules per gram Kelvin, and let's just double check that. Yes, joules per gram Kelvin is what we have. Now, obviously, joules per gram Kelvin, if we multiply that by Kelvin, we get rid of this Kelvin's term over here, but we also want to get rid of this grams term here. Well, what we have is rho V. So rho V, if we do the units of this, it's equal to the units of rho, which is grams per liter. And then we have units of volume, which is liters. So we have units of grams. If we have units of grams here, multiply this by the specific heat, we get joules per Kelvin. Multiply that by temperature, we get just joules. So all of this is really based on how the units work out. So we have our left-hand side of our mass balance equation. Now, what are we going to put on the right-hand side? Well, we want to analyze the effect of a change in temperature from the inlet to some temperature T. And this temperature of the inlet is the temperature of our species A flowing into the tank. So we have kelvins here. Now we want to put rho here. And not VC, but we want this in terms of time. So it'll be rho QC. And I'll try to make this a big C just for nomenclature reasons. And if we do this now, so rho QC. Let's just do a dimensional analysis here. So we have rho, grams per liter, that's our density. We have Q. Q is liters per minute. That's the part that we want to analyze. We want to analyze our change in temperature with respect to time, and our time in this case will be minutes. And we have C, which is joules per grams Kelvin. So grams cancel out, liters cancel out, and kelvins will cancel out once you multiply it with temperature. So what we're left with is a joules per minute. That's the analyzation here. That's our change in energy, our energy balance. So that's going to be in terms of joules. Now, the other thing that we want to look at is we want to look at our energy of cooling. And our energy of cooling is it's going to be on this surface here. Everywhere where the jacket and the jacketed water touches the process, the inside of the tank. And that energy is going to be defined by Newton's law of cooling, which is U, which is an overall heat transfer coefficient, A, which is the effective heat transfer area, T minus TC. Oh boy. This T is the temperature of the process, and this TC is the temperature of the cooling water. So, of course, our process is going to be hotter than our cooling water because, again, it's an exothermic process. So we're using the cooling water in order to control the temperature of the process so we don't have an accidental runaway reaction. What do I mean by that? Well, let's say that we had a non-jacketed tank that was hosting an exothermic reaction. We know that exothermic reactions exert heat, and that heat will increase the temperature of the process, and increasing the temperature of the process increases the reaction rate, and we go in this huge cycle where we aren't able to control the reaction rate of our process anymore. So we'll also tag on this energy, our energy of cooling. So let's add that term on in here. So we're going to subtract this because since it's the energy of cooling, it's not necessarily induced to our process. It's going to be a subtraction from our overall heat, our overall energy balance. So we'll have UA T minus TC. Now the last energy term that we have concerns about is, well, what about our energy of the reaction, which is defined by this KCA over here. Now remember before that we had a rate of reaction. So we have KCA. This has units of moles per minute times liters. And we use this volume to negate that liters. So we want to get back to that same spot. And this will be adding that term this time. So we have volume times reaction rate constant times concentration of A. I need to do a better job at differentiating concentration and specific heat. So let me put this lowercase a. But as it stands right now, this term has units of moles per minute, which isn't joules. However, we have something else that helps us with this energy conversion, and that's our heat of reaction. That's in terms of joules per mole. So we can multiply joules per mole to our moles per minute to get joules per minute. So minus delta H. I need more room here. Hold on. There we go. Minus delta H of reaction, which if you remember, this is an exothermic reaction, and since it's an exothermic reaction, it's going to be a negative value because it is giving off its heat to the surroundings. And putting this little negative sign here helps us keep this value positive and make it a contribution to our overall energy balance equation. So now, as it stands, we have a full drawn out energy balance as well as a full drawn out mass balance. And what we can do now is we can take this to Python, use the solve IVP function, and be able to graph out our change in temperature with time and our change in concentration with time. And I'll show you how to do that now. So now I've opened up a brand new Python notebook. And let's just start throwing the constants in here. We're going to definitely need those. So let me actually throw this on one side so we can zoom in on this, have these side by side. So first thing, we have our Q, our flow rate in. Q is equal to 100, and I'll toss the units in here too, liters per minute. Our inlet concentration, so say CA in 1 mole per liter. So these are just defining all the variables that we have. That should be a capital T, not a tau. For our inlet temperature, so T in is equal to 350 Kelvin. Our volume is equal to 100 liters. Our rho, our density, I'll just put a lowercase b, looks close enough to me, is 1000 grams per liter. Our C, which is our specific heat capacity, is going to be our capital C instead of our lowercase c, 0.239. This is joules per gram Kelvin. Joules per gram Kelvin. I'll call this like maybe like neg HR, something like that. And that will be 5 times 10 to the 4th joules per mole. So 5e4 joule per mole. This E over R, this is going to be used in our Arrhenius equation to estimate our K value. Call this ER, 8750 Kelvin. Our K naught, which if you remember, that's our maximum heat rate that or our maximum reaction rate that we can have for as defined in our Arrhenius equation. That'll also help us find our K naught for any specific temperature. So for that, this will be 7.2. We'll go K0 equals 7.2 E10. And then this is inverse minutes. Go something like 1 over minutes. Our UA, that was for when we did our Newton's law of cooling calculation. That's going to be also 5 E4. This time it's joules per minutes Kelvin. And all of these little parentheses zeros, this is saying at time equals 0, this is what the condition is. And this is going to be our steady state or our initial conditions going into this problem. So we see that the temperature of our cooling at steady state, that's what I'll do here, SS, is 300 Kelvin. 300 Kelvin. Our concentration of A coming in at steady state is 0.5 moles per liter. So I'll go C underscore, it's just CA, why not? CA steady state is equal to 0.5 moles per liter. And finally, we have our temperature of the process at steady state, which is 350 Kelvin. And remember, the process is this whatever is inside our continuously stirred tank reactor. The species A, which we are reacting to get to species B. So go temperature steady state equals 350K. And those are all of the numbers we will need to do calculations here in Python. So the next part now is going to be coding our function that we're going to throw in to solve IVP to find our concentration and temperature graph, our plot. So we'll define a new function. We'll call this right-hand side for the right-hand side of our mass and energy balances, which we'll get to here in a minute. And we're going to give this inputs of time and some vector that we're going to unpack to get our concentrations and temperatures. So we'll unpack this vector. We'll go concentration of A and temperature is going to be equal to whatever vector we had just defined. So that should be a lowercase v. Just this one. Right. So essentially what we're going to be doing is we're going to be giving it an initial value of what our concentration of A and what our temperature is. And that will get unpacked from the vector that we give it in our initial guess. So that should work fine. The next thing we want to do is, and we'll do it here, we want to calculate what our K value is, our rate law constant. What is that going to be? So we defined our K naught, and we had expressed that it's going to be the product of K naught and the e to the power of minus E over RT, capital E over RT, activation energy over the gas law constant times temperature. Now, we see that what we're given here is ER, and ER is actually E over R. So we have an E over R, and we want to get to E over RT. So essentially what we're going to be doing is we're going to be dividing this value by T to get to this value. So that will look something like this. So we have minus ER over T. And that should give us the rate law constant at a given temperature, which is unpacked from our vector over here. Now we want to start defining our dCA and our dt. So we'll start with our mass balance. Now I'll pull this up here just to refresh our memory. So dCA is going to be equal to our volumetric flow rate over V times the difference in the concentrations from the inlet and the concentration of A at time t, minus KCA, which this K we have calculated in our function. CA is going to be given through our vector. So let's code that in here real quick. So we'll go something like this. Q over V, these are both values that have been defined over here in this box, times difference in our concentrations. So our CAN minus our CA, whatever it is that we have unpacked from our vector. And we are going to subtract KCA. So K times CA. And that should give us our calculation for our dCA dt. This will eventually get moved over to the other side as we're going to be integrating over our time that we will define later, but we'll get to that when we get to that. One last step that we didn't really do that I'll just do in Python is we have to divide this entire side by rho VC to get dt, d capital T dt, d temperature over d time, to get this by itself so that we can properly calculate what our dt is. So let's also throw this into Python. So our first term, so we'll call this dt. Our first term was, remember, it was the rho QC, so PQC, and that C is our gas law constant. make sure that I'm multiplying all these. Otherwise, Python will throw a fit. Times our temperature difference between the inlet and the outlet. So go T in minus T. Our second term is a negative contribution, and that's going to be our Newton's law of cooling. So it's going to be our UA times our T minus TC. And TC can be different. We're going to adjust that here. So for right now, I'll just throw in something saying that TC equals, we'll just call it the steady state for right now. But remember that we're going to be adjusting this cooling temperature to mess with our concentration and temperature plots. So right now this is fine, but once we actually start messing with it, we'll change this value a little bit. So we have our Newton's law of cooling contribution now. And our last contribution is going to be our delta H of reaction, so neg HR, times our rate law, so K times CA. Right. Now, what we want this function to do is we want it to return us an array. So np.array, and go something like this. And we want to return our dCA and dt in the order which we put the vectors, otherwise the math won't be correct. So we just want to follow this convention. We put CA and then T. So that's what we're going to do here. We're going to go dCA and then dt. Should be a lowercase, just follow convention. So now we should have a function fully coded out for us to use solve IVP to give us an array of plots over a given period of time, for which we can then plot out onto two separate graphs to show our dCA and our dt. So really quickly, I said I would do this and then I didn't. Just shows you how careful you have to be when doing this. Remember, we have to divide this by rho VC. So P times volume times heat capacity. Because remember, in our energy balance, we had this on this side. So we're just going to have to divide this entire right-hand side by rho VC. That looks taken care of. Now let's use our solve IVP function. So we're going to go sp dot integrate underscore, I believe, solve IVP. Or is it dot solve IVP? Let me look it up. Solve IVP Python. Solve underscore IVP scipy dot integrate dot, yeah, that should be all right. I wonder how did I as SP, so that should be this. So our first thing that we're going to do is we're going to have to define our time range for which we want to analyze this interval. So over here, I'm just going to define a t end. And for now, let's say this is like 10 minutes. Right? So we'll go from 0 to t end. T end. And now we want to give it our, oh no, first we need to give it we need to give the function, right? So we're going to have right hand side 0 to t end, and then we need to give it our initial guesses. And for right now, we're just going to give it our steady state conditions. So first we'll give it our steady state condition for our concentration of A, CaSS, and then our process temperature, so TSS. We're going to choose our method. So our method for this one is going to be the Radan method. And we're going to select our dense output to be true. So we can plot this out as a function of time. Don't think I need this actually. Do need to spell it correct, however. And let's see. Oh. All right, now we see that the solver successfully reached the end of the integration interval, and we have a set of times, and we have our y values. So I'm gonna set up a new t interval, and this is just gonna be for our plotting purposes. And we'll say that this is gonna be a list of linearly spaced points from 0 to tn. We'll say we want 200 data points. Why not? And now let's start doing our subplot. So fig.make subplots. Subplots. And I'm going to want to set this up to have 2 columns in 1 row. So I'm going to say rows equals 1, cols equals 2. Right? And now let's add our scatters. So fig.add scatter. We're going to have x is equal to our time for plotting purposes. Our y is going to be equal to our solution as it is referenced to our new time intervals, our t-plot. So y is equal to the solution t-plot. But we don't want to have both of these. We don't want to have both dca and dt on one plot. In fact, we just want to have our dca in one plot and our dt in another plot, right? So we're going to set this equal to row equals 1. I'm going to set this to coordinate 1, 1. And we're going to name this our concentration of it. And now we're going to do the same exact thing for our temperature this time. This is going to be in row 1, column 2, and we're going to call this temperature. And now when we plot this out, we see a nice graph where we have this downslope here. And for our temperature, it's the same thing where we see it slightly go and increase. This one slightly goes and decreases. Well, the question now remains, why is it changing if we're setting it at the steady state conditions? And the reason for this is because the textbook from which we had grabbed this problem from has some round off errors, which is why it's not necessarily the perfect straight line that we should expect it to be. Since there is a round off error and it's not the exact process conditions that needs to happen for steady state to occur, Python starts plotting out this slight decrease in our concentration and the slight increase in our temperature. However, that's not really what we're after. What we are after, though, is we want to change this cooling water temperature. If remember what our problem statement was, is that we wanted to change this cooling water temperature through the inlet, either change it up to 305 or down to 290. I think I want to see what happens when we bump it 5 Kelvin up. So let's do that. So now that's as easy as plugging in 305 here. All right. Now we see that it starts at 0.5 for its concentration, goes up, and reaches this new steady state around 0.91 moles per liter. And our temperature of the process actually decreases, but never really hits 305. Instead, it hovers around 319 right about here. If we want, we can also look at what happens when we change the temperature to 290. And we see that even when we take down the temperature, we still rise in our concentration, reaching this new steady state around 0.96, and our temperature starts to decrease as it meets this new colder temperature uh, over as we have to find it over here. So I found a little mistake when I was looking back through this energy balance, because we should actually be getting a different outcome when we look at 305 Kelvin, and I'll show you that here in a minute. But you see here that we have VKCA. I believe somewhere along the way that V kind of got gobbled up, and that's not here anymore. That should be there. And now when we analyze our plots at 305 Kelvin, something very interesting happens. You see, now we have this oscillatory behavior that we notice both in our concentration and our temperature. And essentially what's happening is that we're hitting some critical concentration, or we're hitting some critical temperature before our process starts to come back down, and then it rises again, comes back down, rises and rises. So this is definitely not something you want to have when you're simulating a real life tank reactor like this. This is definitely grounds to get fired if you ever set it at these conditions. But this is the pattern that we notice when we analyze this certain jacketed CSTR system at 305 Kelvin using solve IVP to simulate, and using our subplots to visualize what happens here in these tanks in terms of the concentrations and the temperatures.